So, we can also use other register pairs. So, there is one instruction like LDAX. So, this LDAX instruction, so it means that load accumulator extended. So, this one, so this also accepts a register pair as the operand, and then this register pair we can so somehow this register pair, if it is loaded with some value, and then that will be acting as the address. So, copy the 8-bit contents of the memory location identified by the register pair RP register pair into the accumulator. So, this will take the value onto the accumulator. So, it does not put it onto other locations, but it will put it onto this accumulator register. And then this register pair, it can be BC or D. So, I cannot use HL because HL is not necessary. HL is used if I am using HL, then we have got this move instructions, move A comma M or move M comma B. So, like that. So, that HL is much more generic in nature. So, that is already that facility has already been provided. So, what the designers did is, apart from HL, so if you want to use some other address also, other pointer, like so in the previous example, so we have seen that if I want to have P as a pointer, so this P's address is loaded into the HL pair. Now, it may so happen that I want to do star P equal to star Q, where P and Q are 2 pointers. Now, how to do this? So, this somehow this P's address is loaded into HL. Suppose this address is known to be 1000 and this Q's address is known to be 2000. Okay. So, what you do? You first load this HL pair with the value 1000. Okay. So, this HL pair contains the value of this 1000, and then you for P you do for this Q part we do LDAX say D comma no, this will not work. So, first of all, this register pair has to be loaded with the value. So, for that we do say MVI or LXI D comma 2000. So, LXI H comma 1000 loads the address of P onto H register, LXI D comma 2000 loads the address of Q onto the D register, and then I can do LDAX D. So, this will give me the content of location 2000, that is star Q onto the A register, and then we can do move M comma A, so that the content of that accumulator goes to the memory location. So, this way we can do this type of multiple pointers can be accommodated. So, this helps in realizing the pointer arithmetic, this pointer assignments. So, this way we can use this register pairs for this memory access type the pointer type of access. So, this LDAX is one instruction for doing it. Now, indirect addressing mode. So, using data in memory directly without loading first into microprocessor's register is the indirect addressing. So, we do not load the address into some register and then do the loading, okay, then load the address content of that memory location. So, this indirect addressing, it uses the data in a register pair as a 16-bit address to identify the memory location being accessed. So, whatever we were discussing so far, that LXI the move A comma M or that LDAX type of instructions. So, they are actually using this indirect addressing. This HL register pair is always used in conjunction with the memory register M, and these BC and DE register pairs are used to load data into the accumulator using indirect addressing. So, in the previous example we have seen that way, that HL pair can be used for accessing the memory location accessing memory, and in that case we just tell M, and for BC and DE. So, we have to use this LDX and the accumulator has to be involved in the process. Next we look into the arithmetic operations. So, arithmetic operations like say addition, subtraction. So, this addition operation we have got two mnemonics available in 8085, one is called add, another is called ADI. So, add is any 8-bit number may be added, the content of one register and the contents of a memory location. So, you can use it, you can use an instruction like say add B, as I said that this will do A gets A plus B, or you can say like an 8-bit number. So, you can say like ADI some 50 hex. So, that means A will get A plus 50 hex, or you can say like add M. So, where A will get the content of A plus memory location pointed to by the HL pair. Okay. So, that way we can have different types of addition operation. So, it can be added to the contents of the accumulator and the result is stored in the accumulator. So, the destination and first operand, so they are all accumulator. Similarly, we have got subtract and subtract immediate. So, otherwise it is same. So, only it is instead of addition it will do the subtraction operation. The result and the first operand are the accumulator. Next, if we are doing this arithmetic operations with respect to memory, so we can do like add M. So, add the contents of M to the accumulator and the HL pair will give me the address. So, that this I have already said. In fact, all these operations add, subtract, this increment. So, all these operations can be done directly on memory locations by having the proper address in the HL pair. Then this increment and decrement operations. So, this is another class of arithmetic operation. So, this is the content of 8-bit registers or memory locations can be incremented or decremented by 1. It does not need to disturb the contents of accumulator. So, I can simply have an operation like say DCRB or DCRB or INRB. So, like that. So, if you do not have this instruction and if you want to say increment this B by 1, then what you need to do is that move A comma B, then add ADI 1 and then move B comma A. So, this is the sequence that I have to do if I do not have the direct increment facility with the registers other than B, other than A. So, that is why this INR instructions, so they are taken directly, so that they do not involve the accumulator at all. So, there is no need to disturb the content of the accumulator. So, it is directly from the instruction. So, now how can we manipulate the address? Okay. So, we have got 16-bit address in some register pair. Now, sometimes we need to increment or decrement it. For example, if I have got an array, that array start address may be loaded, the array is loaded into say memory location. So, the memory start address is 1000. Now, initially we set the HL pair to the beginning of the array by loading 1000 onto it, but after the first item in the array has been processed, we will like to take the HL pair to the next address. Okay. So, for that purpose, so we have got this INX operation. So, INX, so it will increment the register pair by 1 Okay. So, that way, so it is possible to manipulate a 16-bit address stored in a register pair as one entity and using some special instruction like INX RP, the register pair will be incremented as one entity and the carry is already taken care of. The good thing about this INX operation is that so I have got this say if I have got say INX D. So, this D, so what it will do? So, it will take the DE pair. So, this is D and this is E. So, it will do an increment, but if there is a carry generated, so it is automatically taken care here. So, we do not need to in a program we do not need to take care of it separately, but if you are use INR E operation, then the carry that is generated, again you have to take care for doing that thing. So, this INX instruction has been provided for that purpose, and similarly DCX instruction. So, that is for doing the decrement operation. Okay. So, we have got this INX and DCX operations. Next, we will see some logic operations. So, these instructions perform logic operations on the contents of the accumulator. So, we have got AND accumulator, then this AND immediate, then OR accumulator, OR immediate, then XOR accumulator and XOR immediate. So, these are the different operations that we have. So, AND accumulator with register or memory. So, you can say that you can write instructions like say AND accumulator B. So, A will get A and B. So, I can have this ANA M. So, in that case accumulator will get A and memory location pointed to by HL pair. So, this way we can have the AND operation by BSA, or you can have that AND immediate operation. So, ANI some 8-bit value. So, it is say the 20 hex. So, what it will do? A will get A and with the 20 hex value, that is 0010 0000. Okay. So, this way we can have different types of operations, AND operations, OR operation, XOR operation, and the destination is always the accumulator, and the source is also one of the source is also accumulator. So, there is a complement operation. So, it gives the ones complement of the content of the accumulator. So, all the bits of the accumulator are complemented, and the instruction is CMA. So, it is a 0 operand instruction, because it implicitly means the content of the accumulator will be flipped. Okay. So, that way it is a 0 operand instruction. Other logical operations that we have is the rotate is one category of instruction. So, it rotates the contents of accumulator one position to right or left. So, RLC, so it will rotate the accumulator left. Okay. So, bit 7 goes to bit 0 and the carry flag. So, it is rotate left through carry. Okay. So, bit 0, bit 7 goes to the carry flag, and this bit goes to the accumulator, bit 7 goes to bit 0 and the carry flag. I think there is some example after this. This RLC, so this is what happens is that this bit 7 it goes to bit 0 and bit 7 also goes to the carry flag, and this RAL instruction. So, this bit 7 goes to the carry flag and the carry flag comes to bit 0. So, this is this carry flag also becomes a part of the accumulator, as if the rotation is done by taking this carry bit also a part of the accumulator. On the other hand, this RLC, so this is not taking this this carry bit as a part of the accumulator, though bit 7 is transferred to the carry flag, but this carry flag content is lost that way. So, this in the after the RLC instruction the carry flag content will be lost, but in case of RAL nothing is lost. So, the bit 7 is now stored in the carry flag and the previous carry bit is available in bit 0. So, all other bits are shifted. Okay. So, we have got the RLC instruction that way. So, similarly, we have got RRC and RAR. So, that is rotate right. So, it will be rotated from the right end, that is bit 0 goes to bit 7 and carry flag, and in case of RAR bit 0 goes to the carry flag and the carry goes to bit 7. So, they are there. So, we have got the logical operations. So, in case of logical operations, so we compare the contents of a register or memory location with the contents of the accumulator. So, CMP is the instruction. So, we can talk about CMP register or memory. So, we can have instructions like say compare B. So, so A and B registers, so they will be compared, okay. Or I can say like compare M. So, the A and this memory location HL, so they will be compared. A and memory location HL, they will be compared. So, this way we can have this compare instruction. Then we can have this compare immediate. So, CPI. So, that compare immediate. So, we can have an instruction like CPI say 20 hex. So, here the A register will be compared with the immediate value 20 hex. Okay. So, it compares the 8-bit value with the accumulator. So, the compare instruction, it sets the flags like 0 flag, carry flag and sign flag. So, they are set this compare instruction will set them. So, if the two contents are same, then this 0 flag will be set. Okay. So, if one is more than the other, then the carry flag will be set or the sign flag will be set. So, comparison is done using an internal subtraction that does not change the contents of the accumulator. So, internally, so we will be doing the processor does A minus B. So, if it is compare B, so it will be doing A minus B, and depending upon the result. So, if A and B are same, then the result will be 0. In that case, the 0 flag will be set. If A is greater than B, if A is greater than B, then this carry flag will be set, and if A is less than B, then the sign flag will become negative, and the operation result is negative and the sign flag will be set. So, after this, if we check this 0 carry and sign flag, so we can understand what was the outcome of the comparison. So, accordingly we can say it is greater than, less than or equal to. Okay. So, after doing this comparison, we can put that type of condition checks, and that is done by looking into the status flags. Next, we will be looking into another category of instructions which are known as branch instructions. There are this branch categorization. So, you can broadly divide it into two categories, unconditional branch and conditional branch. So, in case of unconditional branch, so it will tell when this instruction is executed. So, the processor is told that you go to the new address irrespective of what was the previous value. Like if it is so, suppose at present the processor was executing instructions in memory. So, this is the memory, and say it is executing the instruction at location 1000, and here the instruction is jump to 2000. In that case, whatever be the content of the next instruction, so the processor will simply ignore that and it will start executing the instruction from location 2000. It will go to the location 2000 and it will start executing from this point onwards. Okay. So, that is why it is called an unconditional branch. So, there is no condition involved in the process. Okay. So, what the processor internally does is that after getting this instruction and after decoding this instruction, simply the program counter gets loaded with the value 2000. So, that is why the next instruction executed is from location 2000. So, this is the unconditional branch, and there is a conditional branch also, where if some condition code is true, then only it will be going to that address. For example, if I have got an instruction like compare B, and then if I say that jump on equal to 2000. So, if this in this comparison, if A and B register values were same, then it will be jump on equal condition will be true. So, 0 flag will be set. So, equality condition is true. So, in that case only, so it will be jumping to the location 2000. Otherwise, it will continue from here. If the condition is valid, then it will start executing from this point. If if A and B are not same, in that case it will execute the very next instruction and proceed like that. So, that is the conditional branch, and previously what we saw, that is an unconditional branch. So, next will be, so this is the unconditional branch type of instruction like jump followed by address. So, this is the address is a 16-bit address. So, it jumped to the address specified. It is something like a go to that we have in some high level programming language. So, there is another unconditional branch which is known as the call instruction. So, call instruction is similar to the procedure call that we have in high level languages. So, here call address call followed by a 16-bit address. So, this new 16-bit address is a subroutine. So, so it is like this. So, suppose this is the main program that it was executing, and then my this is loaded from say memory location 500 onwards. So, when it came to the memory location 1000, okay, so it is calling a subroutine. So, this is a subroutine call 2000. So, the subroutine is a small routine, so which is loaded from location 2000. So, it starts at location 2000. So, what the processor will do when it gets this call 2000? So, it will be it will jump to the location 2000 and it will start executing from this point onwards. So, as it is executing, when this subroutine is over, so at the end of the subroutine there will be a return instruction, and when this return instruction is encountered, then the control will be going back to this point, that is 1001. So, control will be going back to the location 1001. Okay. So, this is the way the call and return instructions are executed. So, return from subroutine and going into subroutine. Now, this is exactly the point where this stack come into picture, like when it was going to this subroutine. So, in the stack it had saved this return value 1001, and when it came to the this return statement, so it popped out this value from the stack 1001 and loaded it into the PC. So, while going from while coming from this call 2000 to this, so it saved the content of the program counter, which was equal to 1001 into the stack. So, the PC value was this PC value was copied onto the stack, and then PC is loaded with the value 2000, and after some time when the return instruction is encountered, then at that time the PC value is loaded from the stack, so that it goes back to this 1001. This is how this return statement and this call statement they are executed. So, they are also some sort of branching. So, they are all unconditional branching that we have. Now, other instructions that are possible. So, these are the conditional branch. So, go to new location if some specified condition is met. So, ZZ jump on 0. So, go to address specified if the 0 flag is set. Similarly, so 0 flag will be set, as we know that if the value of the previous comparison was equal. So, similarly, JNZ jump on not 0. So, this jump on not 0, it will be true if the address is if the condition the values were not same. So, that is non-zero. Jump on carry. So, this is if the value of comparison the first operand was larger. So, that is the carry flag set. So, jump on carry. So, similarly, jump on no carry. Jump on plus. Okay. So, if the sign flag is not set, and jump on minus if the sign flag is set. So, these are the various jump conditions, conditional jumps that we have in case of 8085. Okay. So, using the carry, 0 and sign flags. Some machine control instructions like halt. So, it will stop the execution of the program. So, this I have told some earlier. So, halt will halt the execution of these statements by the processor, and it will be waiting till the processor is waken up by means of some interrupt or some external procedure. Then another instruction which is there is known as the no operation or knop instruction. So, it as the name suggests, so knop is do nothing. So, it does nothing. So, apparently it seems why do we need this thing. So, as it is not doing anything. So, but this instruction is sometimes useful because you want to delay, you want to introduce some delay into a sequence of operations. For example, it may so happen that you want the next instruction to be executed after a small delay of some fractions. Okay. So, you can put a few knop statements, so that some small delay gets introduced into the system. So, that is one utility. Another utility of this knop instruction is for debugging. So, when you are developing a program, so it may have some bugs. So, what we do? We put some debugging statements in between in the developed program, so that we can halt, we can stop the execution of the program in between, do some checking of this register contents and all, and then resume the instruction. So, what happens is that if this is the program, then in between we put some special instructions that help us in the debugging operation. Now, after the debugging is over, now what is done is these instructions which are basically some sort of interrupt. So, they are modified to knop, so that in the final version there is no debugging instruction included. So, they are all knop instructions. So, this we can very easily modify these debugging instructions by knop instructions. So, without hampering the code which is otherwise generated. So, all the addresses and all they remain unchanged, and only these parts they are modified to knop. So, this way we can have some machine control instructions the halt, knop, etc. So, that are going to be helpful. Now, depending upon the operand, so there can be different types of operands. There, for example, with the implied operand like CMA. So, this instruction is a 0 operand instruction, and the operand the implied operand is the memory. We have got this 8-bit number, the immediate data. So, like ADI. So, ADI, this is ADI 4F hex. So, this is basically this addition operation with the immediate operand. Then we can have some internal register or register operand. So, subtract B. So, the B is a register, or it may be a memory address. So, this is LDA 4000 hex. So, content of memory location 4000 hex will be loaded. So, this way I can have different types of operand: implied operand, immediate operand, register operand, and memory address. Now, depending upon the operand type, so the instruction size will vary. Some of the instructions are only 1 byte long, some are more number of bytes. So, for example, the instruction CMA that we have. So, CMA there is an 8-bit code for that, as we know that all opcodes are 8-bit. So, it is only 1 byte long. On the other hand, so if I take this instruction like MVI A, 40 hex, then this for this MVI A part. So, I need to hold there is a code for this part. So, that this is an 8-bit code, and then this 40 hex is another 8-bit number. So, total I will require 2 bytes for holding this MVI A instruction. Or if I have this LXI H, a 16-bit value, then this LXI H part. So, this will constitute the first byte, and the next this 16-bit part. So, they will be taking 2 bytes. Okay. So, total instruction is 3 byte long. So, in case of 8085, some of the instructions are 1 byte long, some of them are 2 bytes long, some of them are 3 bytes long. So, the instructions which are not having any operand, so they are 0 operand instruction, they occupy only 1 byte. Some instructions they are some immediate data or a memory address. So, they will be having for immediate data, that is the 2 byte instruction, and if you have got a memory address, so that is a 3 byte instruction.